In this video, we're going to look at another example of centroids and moments. The question here is to find the centroid of the lamina whose shape is described below in the diagram, density is equal to 5, by applying the centroid integral formulas. That's part A. Part B is to find the centroid of the same region by applying additivity of moments without integrating, no integrals. And the hint here is the centroid of a semicircular plate, y between 0 and root of r squared minus x squared, is 0 for r over 3 pi. Those are x and y coordinates of the center of mass of a semicircular plate. All right, so we define the top function, f of x, to be equal to 1, and the bottom portion is the bottom half of a semicircle, g of x, is equal to minus root of 1 minus x squared. So part A, let's apply the centroid formulas. Mass is equal to, let me switch color here, mass is equal to density times area. Density is equal to, so that's rho times integral from a to b. And the integrand is f of x minus g of x dx. Mass is density times area. So density is 5. Integrate from -1 to 1. These are the x limits of integration. And f of x is the top function. This is 1. The bottom function is this semicircle, the bottom semicircle, which is minus root of 1 minus x squared. And integrate with respect to x. So the mass is equal to 5. Separating out the integrals and evaluating term by term, integral by integral, I should say, -1 to 1 dx. And then plus 5, integral from -1 to 1, root of 1 minus x squared dx. Now integrating 1 dx, that's just going to be x, apply fundamental theorem of calculus, evaluate from -1 to 1, plus 5 times, well, this is just the area of a circle. The definite integral represents the area of a semicircle with radius 1. So that's just going to be pi times radius squared, 1 squared, divided by 2. So the mass is going to be 5 times applying FTC, fundamental theorem of calculus, put the upper limit in, we get 1 minus 1 plus 5 pi over 2. If we simplify this, we get 10 plus 5 pi over 2. All right, let's look at the moment with respect to the y-axis. The formula is density times the integral from a to b. The distance to the y-axis is x times the area of the rectangular element, which is f of x minus g of x dx. And this is equal to, the moment with respect to the y-axis is 5 times integral from -1 to 1, x times the top function, which is 1, minus the bottom function, which is minus root of 1 minus x squared. So we get 1 minus minus, that's 1 plus root of 1 minus x squared dx. But all this whole integral is 0. Why is that? So we can certainly integrate this and integrate term by term, split up the integrals, use substitution method, use substitution, but we don't have to, because you will notice the region is symmetric about the y-axis. This whole region is symmetric about the y-axis, which means this part is exactly equal to this part. That means the moment with respect to the y-axis will be 0. All right, so we'll talk more about that. The moment is 0. The reason is the described region is symmetric about y-axis, which means the moment with respect to the y-axis is 0. But x bar is defined as the moment with respect to the y-axis divided by the mass. So we get 0 divided by the mass is equal to 0. So, and we also know that the centroid of the region lies on the axis of symmetry. And the axis of symmetry here is the y-axis. That means x bar is equal to 0. The moment with respect to the y-axis is 0. And that simplifies our computations. So let's now find the moment with respect to the x-axis. The moment with respect to the x-axis, according to the formulas, are rho integral a to b, 1/2, top function squared, so f of x, all squared, minus bottom function squared, g of x, all squared, and integrated with respect to x. So the moment with respect to the x-axis is equal to 5 times integral from -1 to 1, 1/2 times 1 squared is 1 minus g of x squared, that's minus root of 1 minus x squared, all squared dx. Simplifying this, we get mx, moment with respect to the x-axis, is equal to 5 over 2. Splitting up the integrals, integral from -1 to 1, 1 dx, minus 5 over 2, integral from -1 to 1. The root cancels out with a square, and we just get 1 minus x squared as the integrand. All right, let's evaluate this integral. So we have moment with respect to x-axis is 5 over 2, integral from -1 to 1, 1 dx, minus 5 over 2, integral from -1 to 1, 1 minus x squared dx. So let's integrate. We get 5 over 2. What's antiderivative of 1? That's just x. Evaluate from -1 to 1. Minus 5 over 2, integrating term by term. Integral of 1 is just x, reversing the power rule. And integral of x squared, add 1 to the exponent, divide by the same. We get x cubed, divide by 3. Evaluate from -1 to 1. So the moment with respect to the x-axis is equal to 5 over 2 times. Put the upper limit in, we get 1 minus 1 minus 5 over 2. Put the upper limit in, we get 1 minus 1/3. Now put the lower limit in, we get -1, and minus 1 cubed is -1 plus 1/3. All right, let's simplify this. So the moment with respect to the x-axis is equal to, this is 1 plus 1 is 2, 2 cancels with 2, so we just get 5, minus 5 over 2, times, we have 1 minus 1, that's 2, minus 1/3 minus 1/3 minus 2/3. So we get 5 minus, now distribute the -5/2, -5/2 times 2, we get 5 minus 5, and -5/2 times -2/3 gives us plus 5 over 3. 5 and minus 5 cancel out, we just get 5 over 3. This is the moment with respect to the x-axis. All right, so we have the moment with respect to the x-axis is 5 over 3. The mass of the region is 10 plus 5 pi over 2. The moment with respect to the y-axis, due to symmetry, is equal to 0. So let's calculate the centroid. X bar is equal to my, moment with respect to the y-axis, divide by the mass. This is equal to 0 because moment with respect to the y-axis is 0. Y bar is equal to moment with respect to the x-axis, divide by the mass. The moment with respect to the x-axis, we found it to be 5 over 3. And the mass, we found it before to be 10 plus 5 pi over 2. So this is the centroid of the region. And this, if we decimalize this, we get 0.093. So the centroid is x bar is 0 and y bar is 0.093. But we're not done yet. There's a part B that requires us to do the same, to arrive at the same answer by using additivity of moments without doing any integration. All right, so now let's do additivity of moments. Let's apply additivity of moments. The moment with respect to the x-axis is equal to the moment with respect to the x-axis of the rectangle plus the moment with respect to the x-axis of the semicircle at the bottom. So the moment with respect to the x-axis by the formula is going to be the mass of the rectangle times y bar of the rectangle. That gives us the moment with respect to the x-axis of the rectangle. That gives us all of this, gives us this quantity. Plus, the moment with respect to the x-axis of the semicircle is going to be the mass of the semicircle times y bar, the y coordinate of the center of mass of the semicircle. So let's find the mass of the rectangle. The mass of the rectangle is simply going to be density times area. The density was given to be 5, and the area you can see from the diagram, length times width, that's just 2. 5 times 2 is 10. What about y bar? Y coordinate of the center of mass of rectangle. Clearly, geometrically, you can see that's just where the diagonals meet. That's going to be 1/2 right here. So we get 1/2. This is y bar of the rectangle. Now let's look at the mass of the semicircle. That's going to be the density times the area. Density is 5, and the area of a semicircle is pi r squared divided by 2. The radius is 1, so we just get pi over 2. So the mass of semicircle is 5 pi over 2. Now, what about y bar of the semicircle? Now, we can't see this geometrically. We're going to use the hint that was provided for us in the question. And the hint was that for a semicircular plate, the center of mass is 0 and 4r over 3 pi. But because the semicircle is at the bottom, we just reflect that and we get minus 4r, minus sign, minus 4r over 3 pi. And since the radius is 1, y bar of the semicircle is simply minus 4 divided by 3 pi. All right, so the moment with respect to the x-axis is equal to mass of rectangle times y bar of rectangle plus mass of the semicircle times y bar of semicircle. All these quantities, we have evaluated them. So the moment with respect to the x-axis, let's just plug them in. Mass of rectangle is 10. Y bar of rectangle is 1/2. That's where the diagonals meet. Mass of the semicircle is 5 pi over 2. And y bar of semicircle, we applied the hint they gave us, times negative 4 over 3 pi. Let me put this in bracket to show that's being multiplied. If we simplify this, we get 5 minus 10 over 3, which comes out to 5 over 3. All right, now let's find the mass. So the total mass is going to be the mass of the rectangle plus the mass of the semicircle. So mass is equal to density times area of rectangle. This will give us the mass of the rectangle plus, and mass of semicircle will be the density times the area of the semicircle. So the mass, the entire mass of this plate, that means including the semicircle and rectangle, is going to be 5 times the area of rectangle is 2 plus density is 5 and area of semicircle is pi over 2. And if we simplify this, we get 10 plus 5 pi over 2. Now, applying the formula, y bar is equal to, y bar is the y-coordinate center of mass of the entire system, the entire shape, is moment with respect to the total moment with respect to the x-axis divided by the mass. We found the total moment. mx is 5 over 3. So there it is. That's 5 over 3. The mass is 10 plus 5 pi over 2. And if we decimalize this, we get 0.093 for the y-coordinate of the center of mass of the system. And you will notice this is exactly the same answer we got as part A. Let's look at part A. Where is part A? There it is. We got exactly the same answer. All right. So now let's find the moment with respect to the y-axis. The moment with respect to the y-axis is the mass of the rectangle times times x bar of the rectangle plus the mass of the semicircle times x bar of the semicircle. So the moment with respect to y-axis is the mass of the semicircle, that's 10. X bar of the rectangle is 0. You can see from diagram the x-coordinate of the center of mass of the rectangle as well as the semicircle is 0 because both of those shapes are symmetric about the y-axis. So x bar of the rectangle is 0 and x bar of the semicircle is also 0. Plus mass of the semicircle, which is 5 pi over 2, times the x-coordinate of center of mass of the semicircle, which is also 0. So the whole thing is 0. The moment with respect to the y-axis is 0. X bar for the whole system is moment with respect to the y-axis divided by the mass. Moment with respect to y-axis is 0 divided by the mass, which is 10 plus 5 pi over 2. And that gives us 0. And you can see we get exactly the same thing. We got x bar equals 0, the x-coordinate of center of mass. And we get y bar to be equal to 0.093, or in exact notation, is 5/3 divided by 10 plus 5 pi over 2. And this is exactly the same answer as we got in part A. Part A involved using the centroid integral formulas. part B, there was no integration. We applied additivity of moments. It's good to know it both ways just so that we have understood the main concepts of the theory. All right. Thank you.